Hi, everyone. Today we are going to be focusing on using the mole concept that we used yesterday. And the only difference that we're going to see is that we're going to be increasing our use of it, and we're going to apply it to a couple different things. So, let's see. The thing that's going to be different today than what we were using before is we are going to be focusing now on compounds. So previously, yesterday, we were converting moles and mass and particles and changing between them, but we were only focusing on individual elements. Now we're going to be looking at compounds, okay? We are also going to be utilizing those same concepts from the previous day. So you'll notice there's a lot of similarities. We're just kind of adding an extra step to the measures. So what we learned from yesterday is how to convert from moles to molecules, molecules to moles, moles to atoms, etc. So when you see this conversion factor, this one that we're going to be noticing coming up very frequently, I can sub out this word particles for atoms or molecules or what we call formula units. So any of these terms can take the place of particles, okay, in this conversion factor. I can sub in whatever word I need to. But I always will remember that 1 mole is equivalent to 6.02 times 10 to the 23rd atoms or molecules or formula units. So in this particular example, we are being told to convert 3.35 moles of carbon dioxide into molecules. So I'm going to need to use this conversion factor up here. So I'm going to start off with 3.35 moles of CO2. And I'm going to add in my units first. So I'm going to do the numbers later. Let's do the units first. So moles will go on the bottom. Molecules will go on top. The reason why I need to put on top and bottom is because moles are going to need to cancel out at some point. So 1 mole is equivalent to 6.02 times 10 to the 23rd. Again, I'm just taking this conversion factor from up here and putting it here. So once I multiply that out, the answer that I get is going to be 2.02 times 10 to the 24th molecules. Okay, and my answer here has 3 significant figures, as did what I started with. So this is good to go. Oops. All right, so now when we see a problem like this, we have some differences. Now we are noticing that we're going to be converting formula units into moles. So this is going to be working a little bit differently. Now we see this word formula units, and we're converting that into moles. So remember, particles can be subbed out for atoms or molecules or formula units. So if you ever see formula units popping up, don't panic. It essentially means the same thing as a molecule. So now we're just going to be working in the other direction that we were working in the previous problem. Now we're going to be starting with 1.77 times 10 to the 22nd formula units. I don't feel like writing all of that out, so I'm abbreviating it by FU. No pun intended. But we are going to put those formula units on the bottom and moles on top. And remember, it's always 1 mole. So that means that 6.02 times 10 to the 23rd is going to go on the bottom. So in this case, formula units crosses out, and we're going to be dividing these two values because one is on top and one is on bottom. This then gives us a value of 0.0294 moles of NaCl. Okay? And again, I want to keep in mind sig figs. This has 1, 2, 3 significant figures, and my answer here has 1, 2, 3 significant figures. Oops. Okay, so suppose I want to be able to go from grams to moles to molecules. But when we were doing this yesterday, when we did this step, the moles to molecules step, we used the atomic mass. We looked on the periodic table. We saw how heavy a mole of something is. So for example, sulfur is 32.066 grams in 1 mole. What's happening now with this step And sorry, I said moles to molecules. I meant this step here, grams to moles. So I was going in the wrong direction. So when we're trying to convert grams to moles, moles to grams, if we're looking at a compound, what we have to do is use the molar mass. We have to find the molar mass. And how do we exactly do that? How do I know how heavy a water molecule is? What is its molar mass? Okay. When we were looking at individual elements, we just looked at the periodic table and saw how heavy they were just by looking at the number that's listed. When we see that we have compounds present, we have to do a little bit of extra work. So let's look at an example of that. When we are trying to find the molar mass of a compound, what we are going to do is use the periodic table as we did before, but now we're going to add up all of the elements that would be in that compound. So for example, if I was looking at water, I would be looking at the 2 hydrogens and the oxygen, and I would be adding together all of their weights to figure out how heavy a molecule of water is. So in this example, we're looking at magnesium nitrate. So magnesium is a metal, Mg, with a 2+ charge. It's an alkaline earth metal. It's in that second column. And nitrate is a polyatomic ion, NO3, with a -1 charge. So in order for me to figure out the molar mass of this compound, I first need to get the formula. So I see that I have a +2 charge here, a -1 charge here. I need those to balance out. So I'm going to bring in another nitrate. What that means is my formula is going to be MgNO3 2. So I'm going to have 2 nitrates for every 1 magnesium. So now how do I figure out how heavy magnesium nitrate is? What I'm going to do is list all of the things that I have going on here and look at how many are in the formula. In the case of magnesium, I only have 1. In the case of nitrogen, I have 2. And in the case of oxygen, I have 6. Okay? So what we do is we look on the periodic table and we look at each of those elements' atomic mass. So if we look at magnesium, it has an atomic mass of 24.3 grams. Nitrogen typically has a mass of 14.0, but we have 2 of them. So that means the nitrates or the nitrogens are providing 28 grams. And the oxygen is 16 grams each, but there's 6 of them, meaning that our mass for the oxygens is 96. So if I take this number, and this number, so I'm adding up these values here, what I see is the molecular weight of magnesium nitrate, that molar mass. How heavy is a mole of magnesium nitrate? 148.3 grams for every 1 mole. Okay? So when I'm trying to figure out molar mass of a compound, I need to do this step. I need to figure out what the formula is here, and then I need to add up all of the things that are involved in that formula. So let's try some sample problems of that. Let's say we're looking at lead 2 hydroxide. So our first step is going to be writing out that formula. I see that lead is Pb, and that Roman numeral 2 means I have a +2 charge. So that's going to be Pb with a +2 charge. And hydroxide is not a plain element. It is instead a polyatomic ion, OH, and it has a -1 charge. So +2 and -1 do not cancel out. I'm going to need to bring in another hydroxide. So this becomes -2. Now the charges will cancel out. What that means is my formula is PbOH2. Okay, so that's our first step. We first have to figure out the formula. From there, we're going to add up how heavy this particular compound is. So we remember from our previous slide that the formula is PbOH2. So I need to add up the leads and the oxygens and the hydroxides. I have 1 lead and I have 2 oxygens and 2 hydrogens each. So if I look on the periodic table and I see what those masses are equal to listed there, lead has an atomic mass of 207.2 grams. Oxygen is 16.0, but there's two of them, which is equal to 32. And hydrogen is 1, but there's two of them, so that equals 2. So when we add up these values, what we end up getting is 241.2 grams per mole. So this here is the molar mass of lead hydroxide. So I know in this particular setup, I can write this a couple different ways. I know that there are 241.2 grams in 1 mole of PbOH2. Okay, so you see how I can set this up as a conversion factor. So just like we use the atomic mass as a conversion factor, now we're using the molar mass as a conversion factor. So let's see how we actually apply this. If we're looking at a problem like this, where we were just working with lead hydroxide, we figured out what its molar mass is. We remember that the molar mass of PbOH2 is 241.2 grams in 1 mole. Okay. This problem is telling me that I have 2.5 moles, and I'm trying to figure out how heavy that is. So if I know that I have 2.50 moles of lead hydroxide, and I know that 1 mole of lead hydroxide weighs 241.2 grams, I can just multiply these two values. And that will tell me that I have 603 grams in that 2.5 mole sample. So 603 grams is how heavy 2.50 moles of lead hydroxide would be. And I'm using that molar mass as a conversion factor here. So let's try another one. Let's say in this case, we're working with molecules, so a little bit trickier. Remember that we cannot directly convert molecules to mass. This is what we're trying to get to. So there is not one set conversion that can take me from molecules directly to mass. I need to convert this to moles first. Okay, so this is going to be 2 steps in order to get to our final product. So we're going to start with our 1.50 times 10 to the 24th molecules of sulfur trioxide. So sulfur trioxide is a covalent compound. It's 2 nonmetals, sulfur and oxygen. When we try to name these, or we're trying to write the formulas, these prefixes tell us what's going on. Notice how sulfur does not have a prefix. It's just sulfur. That means there's just one of them. And the prefix tri means there are 3 oxygens. So sulfur trioxide is SO3. What I'm going to need to do to solve this is first convert molecules to moles. So I'm going to be using Avogadro's number because I can figure out how many molecules are in 1 mole because I know it's 6.02 times 10 to the 23rd, okay? So I always know that conversion factor. That's never going to change. But now, in order to get from moles to mass, I'm going to need to use the molar mass of sulfur trioxide. So I'm going to need to add up the sulfur and the oxygens. There's 1 sulfur, 3 oxygens. Get this out of the way. So sulfur is 32.066 grams. Oxygen is 16, but there's 3 of them, which is equal to 48. When I add those up, that's going to be equivalent to 80.066 grams per mole. So I'm going to use that as a conversion factor now, because now I'm converting moles into grams. 1 mole is equivalent to 80.066 grams of sulfur trioxide. So what I've done right now that we're working with 2 steps, I converted molecules to moles using this first step, using that Avogadro's number. This is very consistent. We don't change this up, okay? So molecules crosses out. I then need to convert moles into grams because I'm being asked to find mass. So moles are going to cross out here, and grams is the unit that is remaining. And I get this 80.066 number by adding up the molar mass of sulfur trioxide, okay? Keep in mind when we're starting to do these multi-step problems, when you are setting these up, always put the number 1 with mole. That way you keep track of where your numbers should go. This answer is equal to 200 grams. Now notice I put that little decimal point there. We were provided with 3 significant figures here in our problem. So I want to make sure that my answer also has 3 significant figures. So I could do that in 2 ways. I could write this as 2.00 times 10 to the second, or I can write 200 point. Both of those are totally fine. It doesn't matter which one you write. They are both equal to the same thing. So let's try another practice one together just to make sure we're on the same page. Okay. In this case, we have a graduated cylinder that contains 50.0 grams of water. How many molecules is this equivalent to? So in this case, we are being asked to go from grams to molecules, but I cannot do so directly. There is not a direct conversion that exists for that. I must first convert to moles and then convert to molecules. So this is a 2-step problem. So we're going to be starting with 50.0 grams of water, which is H2O. My first step is going from grams to moles. So if I'm going from grams to moles, I know that 1 should always go with moles. The number that goes down here is the molar mass of water. So we're going to add that up. H2O is just 2 elements, hydrogen, and there's 2 of them, and 1 oxygen. Hydrogen is 1.00 grams times 2, which is equal to 2. Oxygen is 16. So altogether, the molar mass is 18 grams per mole. So I'm going to put that 18 down here in the bottom. I don't want to put it up here at top because 1 should always go with moles. So I'm putting that down here with grams. So if I stopped this problem right now, I would know how many moles 50 grams is equivalent to. But I need to get to molecules. So I'm going to take this 1 step further, and I'm going to convert moles into molecules. So in this step, I'm going to be using Avogadro's number. Remember, what number should always go with moles? 1. That means Avogadro's number has to go here on top with the molecules. Moles will cross out. Now what I'm going to do is type this in my calculator. I would recommend with these multi-step problems, if you have trouble with your calculator not following order of operations, break this up. Do this step first, then multiply it by 6.02 times 10 to the 23rd. So this answer is equal to 1.67 times 10 to the 24th molecules of water. Here I have 3 significant figures with my answer. 3 significant figures were given to me and provided to me. So that is how we utilize what's called molar mass. So it's one extra step because we're adding up those molecules and how heavy they are, but it shouldn't be all that different from what we were doing previously because we're still having the same number of steps. We just have to add some things up to figure out how heavy that compound is. So if you have any questions, please let me know so I can assist you as much as possible. And you're always welcome to come get some help in Wildcat period. But yeah, that's pretty much all I have to say. So let me know if you need anything, okay? Thank you.